We are going to look at prefix, infix, and postfix expressions or notation. So let us introduce a concept of called as expression tree. Okay, expression tree is a vital concept used in any compiler uh, or an interpreter for a programming language. Okay, expression tree. Now, what is an expression tree? Expression tree is a tree where all the internal vertices are operators. So the internal vertices and the external or leaf vertices are operands. Leaf are operands. So for example, if we have an expression 2 plus 3, the expression tree would be of this form. Okay. Or if we have an expression, let us say 2 plus 3 into, let's say, 8. Now we don't have explicit parenthesis, but what we would have, that first evaluated is 3 into 8 as per the mathematical scenario, and then it will be added with 2. Okay, then it will be added with 2. So in this way, the tree what we get is called as the expression tree. Now let us write another expression and try to build an expression tree first. Okay, so I'll write a tree here. I'll write an expression here. Let us say x plus 3 raised to 4 plus x minus y x minus raised to, let's say, 2. Okay, so this is an expression tree that we need to build. Now, what would be solved first? First thing to get solved will be this and this. So we build the expression tree for these two parts first. Okay, so plus x and 3 and minus x and y. Okay, these are the two parts. Then once the x plus 3 is done, we'll have raised to 4. So 4 and plus should be at same level, and x and 3 are at different level. Similarly, on this side, it will be minus raised to 2. And what is minus? X minus y. Now, further part would be that once these two trees are built, two steps are built, the further part would be that these two caps are combined. Okay, plus, and this plus on the right hand side, and there will be left hand side. The right hand part will be headed by raised to. It will be, so left hand part 2 plus x 3, and the right hand side will be headed by another raised to 2 and minus this x minus y. Okay, so we get this as the complete expression tree. So this is how to convert a expression into an expression tree. Now, what is postfix, infix, and prefix? If we do post order traversal on this tree, we get a postfix form of the expression. Okay. We get postfix form of the expression. What is post order? Means root at the last. Okay, root at the last. So if I do post order traversal on this tree, then I get a postfix form of the expression. What is post order traversal? I go to plus and try to find whether there is a left subtree. Yes. So the next is raise this particular symbol. So this node. So here also I'll check whether there is a left subtree. I go to this plus on the extreme left. I'll check whether there is a plus. Sorry, the left subtree. Yes. So x. So x will be the first element to be visited. Then what is post order? Visit T1 up to Tn subtrees in a post order way, and then visit the root. So x will be checked. Does x has left subtree? No. Does x has any subtree? No. Mark x to be visited. Go to 3. Whether 3 has any subtrees? No. So mark 3 to be visited. Now all the subtrees of this plus is visited. So mark now plus to be visited. So plus is the root of this tree up to this point. So plus is the root of the tree up to this point. So mark this to be visited. Okay, now go to 4 because 4 is the subtree of this raised to exponent, and the first subtree of exponent, that is marked with yellow, is already visited. So now mark 4 to be visited. Okay, now mark 4 to be visited. When once 4 is visited, go back to whether there are any subtrees for exponent. No. So mark now exponent to be visited. Okay, mark means what has happened now? All the subtrees of plus, all the first subtree of plus is visited. So go to the next subtree of plus. So you go to this new exponent. Now this exponent is new root. Check whether it has a subtree. Yes, go here. This minus is a new root. Check whether it has a subtree. Yes, go here. X is a new root. Whether it has a subtree? No. So mark X to be visited. Go to Y. Y is a new root. Whether a Y has subtree? No. So mark Y to be visited. Any other subtree is left for minus sign? No. So go to the root. Mark root to be visited. Go back to the other subtrees of this exponent, the upper one. So 2. Whether 2 has any subtrees? No. So mark 2 to be visited. Go back to any other subtrees of exponent? No. So mark exponent to be visited. Go back to plus. It's the last, that is the original root. Whether any other subtree of plus is to be visited, because the second subtree of plus is also visited. This one. So mark plus to be visited. So this gives us the postfix form of the expression. What does this give? This gives us the postfix form of the expression. So, any doubt? So, in the prefix form, what pre means? Visit the root first, and then the subtree in the order of left to right. So, start from here. Okay, so let's start from here. So, root. So, mark root to be visited plus. Check whether it has left subtree. Yes. So, go to the left subtree. Mark root of the left subtree visited, because it is a pre-ordered traversal. So mark this exponent to be visited. Check whether it has left subtree. Yes. Mark plus to be visited, because it is the root of this subtree. Go to the left first subtree of this. Okay. Mark root to be visited. X. Whether x has any subtrees? No. Go to the other subtrees of plus. So go to 3. Mark 3 to be visited. Whether 3 has any subtrees? No. Okay. Go back. Look for. Go back to plus. Are there any more subtrees of plus? No. So go back to plus. From plus, go to the next subtree of exponent. So mark 4 to be visited. Are there any subtrees of this exponent there? No. So go back to plus. Go to the remaining subtrees of the plus, that is our root of the tree. So go to this exponent. Mark this exponent to be visited. Okay. Does it has left subtree? Yes. So go here. Mark this minus sign to be visited, because it's a new root. Go to the left subtree. Mark this x to be visited. Okay. Any subtree to x? No. Go to the next subtree of minus. So y. Any subtree to y? No. Mark this y to be visited. Go to minus sign. Any more subtree left for minus sign? No. Any more subtree left for the exponent? Yes. So mark, go to here, 2. Mark 2 to be visited. Any subtrace to 2? No. And so this is the prefix form of the expression. So let's do it for the infix notation. So blue arrow indicates infix traversal. So go to the plus, check whether it has left subtree. Yes. So go to the left subtree. Go to the exponent, check whether it has a left subtree. Yes. Go to plus. Check plus whether it has a left subtree. Yes. So go to x. Check whether x has a left subtree. No. So mark the root of the tree to be visited. So mark x to be visited. Okay. Now when x is a left subtree of plus and x is visited, means now root should be visited. So mark plus to be visited. Go to the remaining subtrees of plus. So go to 3. Okay. Go to 3. Any subtrees to 3? No. So mark 3 to be visited. Okay. Any subtrees on the right side of the tree? Any more subtrees? No. So go back to plus. From plus, all the subtrees are visited for plus. So go back to exponent. So mark. So exponent's left subtree is completely visited. Okay. So first subtree is completely visited. Mark exponent to be visited. Then go to the next subtree of exponent. So go to 4. Whether 4 has any subtree? No. So mark 4 to be visited. Go back to plus. Now for plus, its complete subtree is visited. The first subtree. So mark plus to be visited. Go to the exponent. Does it has left subtree? Yes. So go to minus. Does it have a subtree? Yes. Go to x. Whether x has a subtree? No. So mark x to be visited. Mark root of the tree to be visited, whose x is a first subtree. So mark minus sign to be visited. Go to the other subtrees of minus sign, y. So y, whether y has any subtrees? No. So mark y to be visited. Then go back to minus. Any more subtrees for minus? No. So go back to exponent. Any more subtrees of exponent and exponent? So mark exponent to be visited because all its left subtree is visited. Okay, first subtree. So mark exponent to be visited. Any more subtrees for exponent? Yes, 2. Any more subtrees for 2? No. So mark 2 to be visited. So this gives an infix notation. So to evaluate a prefix expression, scan the expression from right to left. Now scan it from right to left till you find the first operator. So scan from right to left till you find the first operator. Now when you find the first operator, then immediately before the operator, the two numbers or two characters will be operands of this expression. Okay, operands of the expression. So this is 2 raised to 3. Okay, 2 raised to 3. So replace this part of the expression with 2 raised to 3's evaluation. So this part becomes 8. 4 will remain as it is. Division 2, 3, 5 will remain as it is. Minus and plus. Now again scan in the second step from left to right and wait at a point where you get the first operator. So this is 8 divided by 4. So when it becomes 8 divided by 4, replace this much part of the expression with 2 as 8 divided by. So now it is 2, 5, 3, 2. Multiplication minus plus. Now again scan the expression from left to right. Okay, again scan it from left to right. So you'll find first operator multiplication. So group the operand. So this will become plus, minus, 6, 5. Again scan the expression from left to right. Now again scan the left expression from left to right. You find first operator. So 6 minus 5. So this becomes plus 1 and 2. Again scan the expression from left to right. now you find that 2 plus 1 is equal to 3. So this is how you evaluate a prefix. Is we have to scan from left to right. Okay, so this is the way we will scan left to right and scan till the point you get the first operator and block the first operator and the two operands. So 2 into 3, it becomes 6. So this will become, so scan from left to right. So this will become 7, 6, minus 4, exponent 9, 3, division plus. Now, again scan from left to right. Okay, again scan from left to right. So what you get? You get the first operator here. So this becomes 7 minus 6. So this becomes 1, 4, exponent 9, 3, division plus. Okay. Then, then again scan from left to right. Okay. Find the first operator. It is exponent. So the two operands will be this. So this will be 1 raised to 4. So 1 raised to 4 will be 1, 9, 3, division plus. Again scan the expression from left to right. So scan it and you find division. So block the two operands before division. So this is 9 divided by 3. So this will become 1, 3 and plus. Okay. Scan the expression from left to right. Scan the expression from left to right. So this becomes 1, 3 plus. So you get plus, we block this and so you get the answer as 4. So scan it from left to right and find the first block. Okay. So 2, 3. Okay. Now this 2, 3 is, this is postfix. Okay. So this is postfix expression. And then to this what we have? 7 minus. Okay. So 7 minus. Means what we have done? We have now evaluated this much part of the tree. Okay. 7 minus. Now if you look at the other part, I have written this tree 7 minus 2 raised to 3. So what we get? 2 raised to 3 will be first evaluated 6. 7 minus 6, it will be 1. Okay. Now, so what I get? I get minus 7 multiplication 2, 3. To this I'll add an exponent. Okay. And it will be 4. Okay, it will be 4. So what I get is this part of the tree. Okay, what I get is this part of the tree. So 4 and exponent. Now if you look at this part of the tree, 9, 3 and division, that is totally different. Okay, that is totally different. And then it is added with this part of the tree. Okay, added with the part of the tree. So this is 9, 3 and division. So 9, so division 9 and 3. Okay, so that's the division. And then both these parts are added. So what you have done, you have blocked this Okay, and then you combine the two parts. How you build a tree from a postfix expression? You can build a tree. Which okay. So consider this graph, and let's name this graph as G. So now spanning tree of G is basically a subgraph of G. Okay, so spanning tree of G is a subgraph of G such that such that subgraph of G such that it is a tree. So how is the subgraph? The subgraph is a tree containing every vertex of G, containing every vertex of G. But it should be tree. And what is the definition of tree? Tree is a graph which does not have circuit. So every vertex should be considered, but there should not be any circuit. So there could be many spanning trees for the given graph. Okay, so A, B, C, it could be D, and it could be F. So A, B, C, D, E, F. So this is one span. Or it could be other way. That is B, A, E, C, D. So B, A, F, E. Okay, B, A, F, E, C, and D. So there could be other spanning trees. So for a given graph, there could be many spanning trees. And to generate a spanning tree from a graph, there are two basic search algorithms called as depth first search. Depth first search. And the second algorithm is breadth first. Depth first search and breadth first.